Hi everyone, welcome back to topic 3, Accelerated Data Science with GPU. In the previous session, we give an overview and introduction on the history of data process evolution and the need for end-to-end data process acceleration. In this session, we will focus on QDF, which is a library of rapids that can utilize GPU accelerated data frame to handle large data. Today's data science problem demands a dramatic increase in the scale of data, as well as the computational power required to process it. Unfortunately, the end of Moore's law means that handling large data sizes in today's data science ecosystem requires scaling out to many CPU nodes, which brings its own problem of communication bottlenecks, energy, and cost. A key part of data science is data exploration. To prepare a dataset for training a machine learning algorithm requires understanding the dataset, cleaning and manipulating data types and formats, filling in gaps in the data, and engineering features for the learning algorithm. These tasks are often grouped under the term extract, transform, and load. ETL is often an iterative, exploratory process. As datasets grow, the interactivities of this process suffers when running on CPUs. To address the challenges of the modern data science pipeline, Rapids was developed to execute an end-to-end data science and analytics pipeline entirely on GPUs. Rapids aims to accelerate the entire data science pipeline, including data loading, ETL, model training, and inference. This will enable more productive, interactive, and exploratory workflows. So why do we prefer to use QDF? QDF was built on the Apache Airflow columnar memory format. QDF is a GPU data frame libraries for loading, joining, aggregating, filtering, and otherwise manipulating data. QDF provides a pandas-like API that will be familiar to data engineers and data scientists, so they can use it to easily accelerate their workflows without going into the details of CUDA programming. At its core, QDF is really a low-level kind of C++ in CUDA implementations to be able to use the hardware as effectively as possible, along with Python bindings on top of it, to make it look and feel like pandas, which data scientists are used to using and are comfortable using today. And so, the lower level library called libqdf, it has a full C++ API that users can use, and then has all the CUDA kernel implementations underneath. It exposes things like sharing data frames across processes using something called CUDA, inter-process communication handlers, and then has kind of the things that you would typically expect in the data frame libraries, like element-wise math operations, sortings, joins, group by, etc. And then in the Python side, it kind of has all the things that you are used to do with pandas. like integration into the rest of the PyData ecosystem. And so you can like interoperate on things like NumPy and Python structures and similar. And we also heavily use a library called Number. As an end user, instead of using like .apply and pandas and having to execute in pure Python and be really slow, that you can do the same function and it actually gets compiled down to GPU code and gets up like run at essentially the speed of hardware. And then this is all run on top of the Apache Arrow data structure. And so integrating with kind of the rest of the big data ecosystem. And the PyData ecosystem is really as simple as just copying memory to and from the GPU. Well, let's talk about some of the challenges that we have to deal with. So the aim is to do accelerated GPU performance, with the flexibilities and the breadth of functionalities of libraries like pandas. So we have to bridge dynamic language to static languages, C++ and CUDA C++. This is a challenge because we have to support operations on tables with a broad range of data types, arbitrary numbers of columns. And that means it's important that we have flexible runtime, dispatch on different data types, which is something that's natural in a dynamic language like Python. But in a statistical compiled language like C++, you need to work hard to make sure that this doesn't cause you to suffer extreme compiled runtimes and extreme binary sizes. Because you know, if it takes 8 hours to compile the libraries, or the library as a gigabyte or even 10 gigabytes, just because of the different combination of data types that we have to support, then that's a non-starter. We also have to support missing and invalid data. It basically enables us to support datasets that come in with missing data, or NANs, or etc., and enabling Python user-defined functions to operate on data frames on the GPU. We will be developing some interesting solutions on that by compiling just-in-time compilation using Number and injecting the assembly that we get from that into C++, which we can then just-in-time compile for the GPU. And then another major challenge is high-performance memory management. We are dealing with very large data set across multiple GPUs. Also, there's a high frequency of allocation and deallocation because often the data frames are immutable. So when we perform an operation on it, we get a new data frame out. And so we need to be able to do that efficiently. So we've built a high-performance sub-aggregator on top of CUDA to enable that. This page shows the performance benchmarks for QDF. This is a single GPU speedup compared to pandas, while all the bars are speedups of GPU versus CPU. And the dark blue are speedups for larger data frames. So 2 columns of 100 million rows versus 2 columns at 10 million rows. They are all double precision floats or 60-bit floats, and you can see speedups from 30 to 60 times on large data frames. This is for group by, merge, which is like a join, and sort operations. And it is running on NVIDIA DGX1, which is a server that has 8 Tesla GPUs. But here we are just using one of them for this benchmark, and it has Intel Xeon CPUs. QDF also provides string support. String support is really important for a lot of data sets and a lot of analysis. Currently, Rapids have regular expression support, and we can do element-wise string operations like splitting and finding, concatenation, etc. We can also do group bys and joins and sorting on string columns in data frames. And in the future, perhaps there will be more string support to improve it. The current QStream library will be combined as part of libqdf so that we can get better integration and reduce code duplication. Some of the current limitation of QDF on categorical string columns will be the performance and compatibility issues. And hopefully, these issues will be resolved in the future improvement versions. Another big part of accelerating data frame is accelerating the I/O, input and output. So being able to load different file format into GPU memory and do it fast. The example here is showing comparing loading a 2 GB, actually it's a 1.9 GB CSV file, which is a taxi trip data set using pandas versus using QDF. And it's about 29 seconds using pandas and 2 seconds in QDF. And there are also CSV writer, Pocket reader, JSON reader, other readers, and HDF5 reader. So the key to getting this performance is to accelerate both the compression, if it's there, and also parsing, and doing all that on the GPU. So Rapids enable us to scale up from CPUs to GPUs, the PyData ecosystem effectively by pandas scikit-learn. We can also accelerate NumPy using a package called QPy, which is from part of Rapids. And number is another big part of that. But we also want to be able to scale out so that we can really handle big data problems. And so to do that, we are leveraging Dask, which is a package, actually a Python package for distributed computing, which can scale from to all the cores of our laptop or to all the nodes in the computing cluster. And with Rapids, we can use it to scale to all the GPU accelerated nodes in the cluster, and combined with another package called OpenUCX, which is an interface to hardware, networking transport, such as TCP, NVLink. NVLink is a video interconnect between GPUs and things like that. So in that way, we can scale up efficiently and not to be bottlenecked by communication problems. And that's the end of QDF.